Hey folks, Adam Dupay here, and in this video we're going to be doing a live hacking of the pwnable.kr challenge UAF. So looking at this challenge, we see it's named UAF, it's 8 points. It says, Mommy, what is use after free bug? SSH UAF at pwnable.kr, so we know it's on the site. So this presumably based on the name of the challenge and by this description here, it's clearly going to have something to do with use after free, which is a type of heap bug. So let's look at the challenge. So we get in here and we can see again we have a UAF binary with set UID group of UAF underscore pwn and CPP code. So here we have C++ code, that's interesting, and the flag. So let's look at this code. So class human, private virtual void give shell. Well, that sounds interesting. That sounds like maybe that's where we want to target. Protected, age, name, public, virtual void, introduced. My name is name and I am 8 years old. Class man, subclasses human. I guess I should preface this while I'm reading this. It's been quite a long time since I've had to deal with C++ code. So I'm definitely much more of a C guy than a C++ guy. So this will be interesting. All right, so the class man, which subclasses humans, has a public man, string name in age, sets the name and the age, and introduces themselves. So that would mean what? Every human has a function give shell. Okay. We have a man. I'm a nice guy. We have a woman, which introduces themselves and then outputs I'm a cute girl. Why does the guy have to be nice and the girl have to be cute? I think that's silly. Okay, so int main, we have a human, so the important thing, so now we know when we're reading this, we need to think about, we kind of already have a goal state, so we need to somehow call this give shell function or trick the program to call that. And what we have here is we have new, so we know that because of the name of the function that UAF, use after free, is going to have to deal with things on the heap. So from what we know, so in C, malloc and free are the methods that actually will allocate things onto the stack, and then, onto the heap. So specifically not on the stack. So there's a point, so an interesting thing to note here, so all this data, this size length, this character pointer data, this op, all of this is stack allocated data. The new keyword in C++ causes this to be allocated on the heap. So this is going to go through the heap allocation. So it's going to allocate a new man, name of Jack, age 25, a new woman, name of Jill, age 21, and is going to give us a menu. So it's going to say use, 1 use, 2 after, 3 free. Okay. So we're just going to keep doing this forever. So this is an infinite loop here, and it's going to say switch on the operator. Case the operator is 1, the man, the M variable introduced themselves, the W variable introduces themselves, and then break. So we know that introduce gets called here, and so outputs the name and the age, and the little something about them based on the inheritance here. Output 2, it's calling the after. Okay, this is pretty easy. Okay, I think. I mean, not easy, but this will be interesting. So we know we have to do a use after a free. So 1 uses the variables M and W. Case 3 is the free. So case 3 is actually deleting M and W. And an important note is that this doesn't change these pointers. So remember looking here, so M is actually, the type of M is a human pointer. So it's a pointer to a human object. And when we delete M, what the heap does is it frees that memory location that is there on the heap, and it's going to free that memory but not change the pointer. So this pointer, this human star M, this is actually still pointing to that memory location that's on the heap. And then if we look at case 2, so case 2 is going to read a length from argv1, and it's going to create in data, so it's going to allocate on the heap a new character array of the size of the length that we want, and then it's going to, interesting, it is going to read, it's going to open argv2, read only, it's going to read that data. Okay, so what is this doing? So basically argv1 is going to be the length of data, argv2 is going to be the name of a file that we want to read from, and then it's going to say your data is allocated, otherwise break. Great. Okay, so the idea is, what do we want to do? So what we're going to want to do here, the question is, can we actually call this give shell? I'm not sure. But what we know is this give shell function should exist somewhere in our program. And this is when I'm going to probably have to learn about vtables and everything to be able to do this. So essentially what we want to do is have it when we call this mintroduce, we actually, instead of calling the introduce function, we want to get it to execute system bin.sh. So the other thing let's open this up in GDB. The other thing I want to find out is, I want to figure out what kind of operating system they're running. So it's for blah, blah, blah. And actually what I really want to do is figure out what libc version are they using. Like what's the malloc operator, but that's okay. We could do this. And let's also boot up in our handy dandy hopper. Let's open this assembly file in Hopper. So we are at UAF. Great. So what I'm looking for here, basically what I'm going to want to do is I'm going to want to look at, where we go to. So what I want to do is I'm going to look at this code here and I want to find out where's the code that's calling this case 1, where it's going to introduce. And what I'm going to want to do, because that's going to dereference the M pointer and then it's going to go to some offset and then it's going to jump there. And what we're going to want to do is in our input, we want to create something that at that offset will have a pointer to go to this system bin.sh. So here we can see it's actually pretty easy. At least the binary here. I haven't, like I said, I haven't spent actually any time really looking at C++ assembly code, so this will be definitely a bit of a first for me. So we can actually, there we go. We already found it here. So it's dereference variable 38, which is probably the M variable. Plus 8, so go 8 from that, dereference that, and then essentially call that as a function. So let's look for that actual code. So this would be, we'll change it into this mode, so this should be able to tell. So this is compare if it's 3, if it's, oh interesting, it does this, that's interesting. It's calling the destructor function, interesting. Okay, compare it to 1. Aha, here's the code we want. So this is, so I'm going to rename this to M to know that that's our M variable, and I'll rename this to W. I don't really care about W really at all because we should get to that function here. So let's walk through what this does. So it takes M, so remember M is a local variable that's on the stack that is, let's see if this will tell me exactly where it is. It's at, well, I can find it out. It's some offset of EBP, or RBP in this case, since we're 64-bit. So it's going to move that into RAX. It's going to dereference that pointer. So now it's going to point to memory that we control. It's going to move whatever's at that current location into RAX. It's going to add 8 to that. So it's going to move 8 bytes down. It's then going to dereference that, move it into RDX. And we can see here it's going to then call RDX. So here it's setting up the parameter that it's passing to RDX, but it's going to jump to this function. So we want the variable that's going to be in this call RDX register, we're going to want this to be that system. And we can actually easily find where this is. So we can go to system, we can do a cross-reference, and we can see here is the function for human give shell. So if we get here, then we will, and we can make this nicer by telling Hopper that all of these things are strings, which I think, there we go. All right, great. Let's save this, UAF hop. Okay, great. So we know that this give shell. So essentially when we think of it, this is the address. So this is our target address. So what I'm going to do, we're going to start creating an exploit for this. And again, we're going to use pwn tools. And again, I'm going to steal some exploit that I've already written. And this should be process. And you know what we'll do? We'll actually, rather than specifying it, we will do sys.argv1. And so this is what we want to jump to, right? This 0x. So if we can get, so think about it this way, if we can get the control flow to execute here, we will call system bin.sh, which is exactly what we want. And we know, so basically what we know is that, going back to this code, what we know is we can actually completely control the heap. So we can make it so that the heap value, so I guess it is a question of whether we'll be in the first, whether the pointer that we'll have will be the first one or the second one, but we can actually debug that and test that fairly easily. So we're going to delete W, delete M, this new allocation. The other thing we need to do is we need to figure out what's the, do we need to do that? The size of W and M? Maybe. I think we may be able to just do this by giving it input of, let's say we need 8 bytes off the start, so 8 bytes and then another 8 bytes with this pointer that we want. It should be, yeah, we're 64-bit, so it should be 8 bytes here. That's the pointer that we want, and that's what we'll end up jumping to. I wonder if that would work. Let's see. All right. Let's see. The input here is interesting because it's going to read from a file. So we'll actually need to, in our exploit, create a file in maybe /temp or something like that. But what we want to do, so we already know what we want to do, what our target is. So we know where we want to go. Let's look at main and let's look at, yeah, so W's at -48 and M's at -56. So let's see, it is going to allocate, it's going to call Jill, let's see. Man, this code, when you look at it, is pretty complicated. Okay, so new man, Jack. So where is, so we want to know where is M used, because that's the thing we're going to want to. So move RBX into, so RBX. Okay, so this call, this function call looks like the constructor. Yeah, so we can see man string int. So this is the constructor that's getting called. So that constructor is getting called, and then the constructor for woman is going to get called. So at this point, the stack should have, so if we breakpoint here, the stack should have for M and W the pointers that we want, or the should have for M and W the values, the stack values that we want. So let's break on this value. Let's run it, and let's see. I don't know exactly what I want to put in, so and we'll just do dev. Yeah, I guess I can use dev standard in. Use the proc file system, proc self fd0. So read 10 bytes. Actually, I want 16. Let's just try that again. That'll read 16 bytes from standard input. Okay. So now we're here. So we can actually look, so we're seeing some of the stack here, but we're not seeing necessarily enough. What we want to see from the stack is we want to see from EBP or RBP minus 56. So, and it needs to be like really wide hex because we're using 64-bit, so pointers are now 64 bits. So I actually don't remember the syntax to do that, but we will find it out. Okay, so let's see. RBP minus 56. Okay, that's not what I want. Can I just keep putting W's? No, apparently not. GDB output 64-bit format. Okay. So while this is going, debugging with GDB, output formats. Yeah, there we go. Yes, that is what I want, but I want also the format, yeah. A G, that's what it is. Giant, 20 giant numbers in hex. So why did I do minus 46? I think that's because that was wrong. We want 56. All right, so this pointer, so now my pointer is here. So I have a 614C50. That would be M, and 614CA0, this is going to be 48. And so what this is going to do is it is going to, yeah, so so these are the pointers that I care about. So these are pointers onto the heap. And if we look at this, we'll see that at this memory reference, so we dereference it, and then what did that code do? Let's look at the code because I want to see where it actually calls on 1. I was looking at that. That was right here. Okay, so it takes this, it dereferences that, it dereferences it again. So there's a pointer in there, then there's a pointer into here. Interesting. Okay, so it's going to take that, it's going to dereference our pointer into RAX, it's going to dereference it again. So our input, okay, so this is when we need to make nice diagrams for what we want to happen. So the current thing is, so in the variable M, there's a pointer onto the heap, and at that memory address, we will then dereference that. So that would be this nice person, 20GX. There we go, and that's, so that's going to be the virtual table for what we want. Oh, okay, this is actually, I think, easier than we think. Because it's going to take that, and then it's going to add 8. So that's going to be here. So this is going to be this table. I believe these are all pointers to all of the functions in man-human. So this is the virtual table of where it figures out who to call what. So I believe these are all at fixed locations in the memory. And I think we could find these in Hopper if we wanted to. So we go here, and it's not going to take this first element. It's going to add 8 to it. So it's actually going to take this next element, and that is going to jump where it wants to go. So actually, all we need to do is put 8 bytes in here, and we need to have that value. So we want M, because we're going to be overwriting, I think, where M is going to be. But this value we want to put in here. So this is actually a pointer to, let's see, +8. So if we do x20i, bang. Yeah, this is introduce. So this is int. What we want to have happen, so this is essentially going to all go away. So this is going to be freed, and we will be able to overwrite this value. So the goal is to overwrite this value to a chunk of money. So actually our destination was not correct. We want to overwrite this value so it points to some memory that has already the value that we want into, what do we call that guy? It has a name. into give shell. I'm going to call it GS. So give shell. So that's where we want to change this to. And so the way we can do this pretty, let's see, easily. So we know we want this. And we can look at where, here it is. So we can actually see at, so at this memory address, so at, yes, okay, but we want -8. So at this memory address, 401.588, 401.588. So at here, +8. So if we put this value into here, we will now be pointing to a memory region that 8 bytes offset is the give shell function. So that's what our target is. So let's continue. Oh, the other place I want to put a breakpoint. Okay, so this is actually the target. We want to jump to this. To do that, we need where M or W points to be that location. All right, awesome. So now what I want to do is I want to debug that. I want to set a breakpoint on the, where's my hopper? I want to set a breakpoint on the free. So I want to see what happens on the free to show you that the stack variables are not going to change. And then I want to set a breakpoint on the read because that's, I think, going to be pretty interesting. So this is the delete. So that is interesting. It's calling the delete. Okay, so this should be the delete right here, right after delete. And let's go to here. Yes. All right. Break star that breakpoint, and then the other breakpoint I want is on after. Here we go. So this is all this pointer fun stuff. Let's see, what's the C code of this thing like? Length data, C out, your data is allocated. Okay, great. So right before the C out call. I think it's going to be right here is what we want. Oh, I don't want that. I want here to get this address. Okay. All right, and continue. So now we have the menu. So we saw we've already allocated those. So we can use them, and we can see it says, my name is Jack. I'm a 25-year-old guy. I'm a nice guy. We have, my name is Jill. I'm a 21-year-old. I'm a cute girl. Then we're going to call the free to get rid of them. And we should be able to see at, there we go. So at RBP -56, we have the two values here. And if we inspect 5GX at that memory location, so right now there's nothing there, right? So that data has actually been cleared. That's interesting. But we still have this pointer here. So let's continue. And now we'll call after. Use, yes. After. And now it's waiting for input from us because remember we gave it 16 bytes, so it's going to look for 16 bytes. And let's see, print a times 16. Okay. So, and because we passed in the parameter slash, what was it? We did slash proc self fd0. So it's actually going to read from standard input rather than a file. So now it should have just copied 16 A's on there, and let's do, why did it continue? Let's just break it now, and let's go up, 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 up. Okay, we're in main now, and let's look at the RBP. There we go. Cool. So we still have these pointers here hanging around, and if we look at this pointer, okay. So here is where our values are. So well, then what's W? All right, let's see. RBP, so this is why you always want to debug things, because you never know how it's going to go. Okay, so the woman, the problem's going to be that if the, where are these laid out on the stack? So M is the one we were using in W. But the problem is M is being dereferenced first. So we'll get a null pointer exception because we're trying to dereference this null parameter. So let's continue. Oh, it's waiting for input from me. I want standard input. Do I want two? I want to, use. So yeah, it should blow up because it should say that RAX, print that's X, sign RAX, P/X is 8, so it's the value 8, so it's a segmentation fault here. Why did that actually work? P/X. Let's see. X/20X. Yeah, okay, so it should take this, so it should take that minus 38. It should... Oh, right, because that is a memory address, and then it should add... Oh, it adds... It takes that, puts that in there, it then dereferences this, and puts that in there, but why would this? Yeah, it should be there. Not exactly sure why this didn't blow up. I'd have to debug this a little bit more. Okay, so this is interesting. So there's a slight wrinkle from our plan. Okay, so so it moved that into there. So dereferenced it one time. Okay, I'm getting... Okay, so it dereferences... so it moves that value into RAX here. It dereferences this to get this value here. It adds 8 to it. Okay, so this actually... Then we'll need to change our exploit. So because the success that we wanted to go to was in... I need a calculator. Guys, give me a calculator. Should be very easy. Okay. Oh yeah, this is what we want, because plus 8 from this is 401, 1590. Is that correct? Let's see, x20, gx. No, this is the value that we want. So we want this minus 8, because it's going to do 8. It's going to do an arithmetic operation. So rather than get the thing that's after it, I believe, where are we? All right, we're going to have to debug this a bit. Let us, what do we do here? Okay, so we know we can control W. The problem is, so what if we allocate more memory? So what if I allocate, so what's the size of these objects? So we should be able to find out by looking in here and go into the, let's see, where's the allocator? I wonder if we could just do it by running maybe ltrace UAF. So it's calling start this after free z string traits basic stream. Man, this is super annoying. Oh, I'm gonna guess it's 24. Yeah. I'm going to guess that this function is the allocator, maybe? Yeah, C15. Yeah, because it's giving different values every time because of the ASLR changing of the heap. So I think what we want to do, let's restart this. Now we want 24 bytes, which should have, the allocator then should put us right back in the same position that we were in. Or maybe, yeah, let's try this. And then we will continue. Let's look at the stack RBP minus 38. So we can see that, remember when you're executing things in GDB, GDB disables ASLR by default. So these memory locations are fixed. So then let's, all right, so let's continue here. We will use, to show that we can do that, we will free and show that we're still here. We still have these memory addresses. We will continue. We will call after. So now it's waiting for bytes from us. And last time, so the problem was I gave 16 and then an enter, which means when it hit that breakpoint, it hit enter to continue. And so since I asked for 24, I'm going to do 23 A's, and then my new line character should count as an A. There we go. So now we'll actually stay. And now what we can do here is examine the heap and say, okay, x20gx, what does this heap look like? Okay, so it's definitely putting our data inside the other heap address. And I'm sure this would make sense if you looked at it about why it would do this. So now the interesting thing would be, what happens if I ask for 48? Ideally, the allocator should say, hey, yes, look, I have a ton of space. This should definitely work. So we'll see if that's the case. Let's free it. Let's look at our heap, same values, good. And we'll call after, and now I need 47 A's. So many A's. All right, and now look at these values, and now show me 50. So I did not get any of that. Interesting. Oh, I know what I can do. I know what I can do. So, so I think it's probably doing it. Let's look at the, if we look at the code here, we would see that your data is allocated. So we can keep calling this. So we can allocate, yeah, this is great. So now we can allocate 24 bytes and basically just completely overwrite what we want. So we'll do this 3 times. So let's restart with our 24 because we want to completely control and make sure we get in the proper spaces. So it's going to do everything else. Let's free everything. Let's continue. We'll call after once. So now I need 24. I need 23 plus an N. Bang. We get there. Your data is allocated. Now let's do it one more time. And let's do, we have this and then a new line. And now let's examine the stack, make sure these numbers are the same, and let's get C50. So now we can see that our data got allocated exactly where we wanted. So we were able to overwrite and control both things. So the idea is because the heap is allocating space on the heap for 24 bytes and then 24 bytes, and then when it frees it, it says, hey, these memory regions are free. So if we then reallocate and say, hey, we want 1 byte and 1 byte, or we want 24 bytes and 24 bytes, it'll actually put it in exactly the same spot. So this is great. So I think here we definitely have an exploit. So what do we want to do? We want to go to, let's see. Okay, at least we can set up now the what we want to actually be our thing. Okay, so we actually want connection process. How do I pass in argvs to connection process? I can look for pwn tools and look at process, and it will definitely tell me. Tubes. Gotta process the tubes. All right, process. Ah, there's nice an argv list. There's an example. Process. Oh, you can just pass in arguments here. Great. Okay, so plus space. Always want to read in 24 bytes from proc self fd0. So this will actually give us the ability to, if we wanted to, now we could change what values we actually write in, which is pretty cool. I don't think we necessarily need that, but hey, it is pretty cool. Oh, you know what? Let's do it like this. This will be a little bit nicer. 24. That. Bang. Now we got a connection. Connection. All right. So let's play this game. UAF 24. And there we go. And connection dot till 3 dot free. It's always just good to get into the habit of making sure that you're synced up in what you're sending and what you're receiving. So we wait until free. We con.send line. We are going to send a free. And then receive until we get the free. So great, it'll tell us that, hey, so we will do 3 enter. It will give us this thing. It will then, we want to say 2, 2, and then now send our payload. And then after we send our payload, so right now we'll just do send a, let's see, P for our payload is going to be equal to A times 24, so we want 24 A's. We're going to send P, so that will send all of that, and then we will 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 18, 19, 20, 21, 22, 23, and enter. So now we should receive until free again. Connection, send line 2. So now we're going to allocate another 24 bytes onto the heap. We're going to send P, and then we're going to call, let's see, we want our receive until, send line use, and after that, let's turn this baby into interactive. And we should be good. Okay. Now the trick is going to be setting up this payload. So right now this should crash the program. Right, so now got end of file in interactive mode because it should tell us that, yep, ended with a sig7. So we were able to send, we sent 24 bytes, so at least our interactions now are all good. And what we want now is what value to write in. So let's go back and review that line, the overwrite, so we can know, we kind of know what we want, but let's make sure we got that. So this is the value, so then here, this is the value then that we control. So it's going to take in the value that we control, it's going to add 8 to it, and then it's going to dereference that and then jump to it. Okay, so this is where understanding your point is really important. Okay, so it's going to take this value, so it's actually going to add 8 to it and jump there. Okay, so I think we actually have had the right value in here. So what if we send, let's see, P32, P64, so this will turn this value into the proper endianness, 64 bits, and we want 24 divided by 8. It'll send that many times rather than me having to do math. Hey, why should I do that? Oh, there we go. That worked. Awesome. All right, man, it's always super good. So that's because we know that at this memory location, so if we go into Hopper, and Hopper is here, and we look at this code, and we navigate, go to address, we're going to go to this address. Let's see, these are all function pointers. I wonder if there's a way, there's probably a way I can tell it that, but I can look at it in the debugger. That will be nicer. So x 20, y g x bang. So what that's going to do is add 8 to this value that's in there, is going to jump to that, and is going to execute that. So now all we got to do is take our exploit, make sure temp atom d uaf, Python exploit, and we want home uaf. What is going on? So is it just slow? What is it doing? I mean, the output that I need is pretty easy, so I can actually just do let's see, where was my local copy? So what is it sending? And that is crazy. Why that's not. Let's print our payload. Representation of our payload. This will actually. There we go. So now we can tell Python to output this to a file. Let's do Python-C print this nice pert thing, and then now we should be able to just do home uaf with 24 and test. So free after use. Interesting. Okay, cat. Let's run ID. Cat home uaf flag. There we go. Your yay flag after pwning. This is interesting. I don't know why pwn tools wasn't working there in sending the data to and from, but you know, that's all right. We got the solution. And so that's all that matters. So we will log in. So that was actually really fun. It's been a while since I've done heap style vulnerabilities, and it's definitely been probably many years before I've actually looked at C++ code and looked at how the object orientation is actually implemented in C++. So I really enjoyed that level. I thought that was super interesting and was a really fun level to do. So thanks everyone. Hope you enjoyed the video. Keep hacking.